This video is going to cover section 5.3, the exponential distribution. So the exponential distribution is often concerned with the amount of time until some specific event occurs. For example, the amount of time beginning now until an earthquake occurs has an exponential distribution. Other examples include the length in minutes of long-distance business telephone calls, the amount of time in months a car battery lasts, and it can be shown too that the value of the change you have in your pocket or purse approximately follows an exponential distribution. So here we have a graph of an exponential distribution. And again, this curve here is the probability distribution function. And the area under the curve represents the probability. So in this case, this graph shows that the area between 2 and 4 is shaded to represent the probability that the value of the random variable x is in between 2 and 4. So with exponential distributions, there are fewer large values and more small values. That's why it's higher over here where the numbers here are small. So the amount of money customers spend in one trip to the supermarket follows an exponential distribution. There are more people who spend small amounts of money and fewer people who spend large amounts of money. Exponential distributions are commonly used in calculations of product reliability or the length of time a product lasts. So more last for less, a few last for longer. So if x is a continuous random variable that is known to have an exponential distribution, then we write that like this, where x tilde exp, and we have the parameter this time m, where m is the decay factor. And m is equal to 1 over mu, where mu is our mean. So this is how we write the distribution when it's an exponential distribution. So in the exponential distribution, our standard deviation sigma is equal to our mean mu. And we can use the Excel command to find the probability that x is less than some number s with this function here, expon.dist. And the arguments we use are s, the value we're looking for. Lambda is what Excel calls it, but that's our m value. And that cumulative number is just like we've seen with the binomial distribution, where we use true for less than and false for equal to. Now, less than or equal to, I didn't write it here, is the same as less than. So we only have that situation or the equal to situation. So examples 5.7 and 8, let's let x be the amount of time in minutes that a postal clerk spends with his or her customer. The time is known to have an exponential distribution with the average amount of time equal to 4 minutes. So x is a continuous random variable since time is measured, and we're told that our mu equals 4 minutes. So we're going to find mu, we just did, sigma and m. We're going to write the distribution. We're going to find the probability that a clerk spends less than 5 minutes with a customer, and the probability that a clerk spends between 4 and 5 minutes with a customer. So we know that mu is 4, and that because it's exponential, we know that sigma is 4. So then m is 1 over mu, which is 1 over 4, which is 0.25. When we write the distribution, it looks like this, and we say x is a random variable with an exponential distribution with the parameter 0.25. And now when we're doing our probabilities, I have an Excel spreadsheet. Let's see if I can find it amongst all my things. Those are for the uniform, but here we have our examples for our exponential distributions. And so you can type in your mu. You can find your m. You can say 1 divided by mu, or, okay, I didn't do an equation, so it didn't let me do that. So I can either do equals 1 divided by 4, or I could just type 1 equals 4. And now we're going to look at these different probabilities. So find the probability that a clerk spends less than 5 minutes with a customer. So that is P, x is less than 5. And we're going to type in this command in Excel with the number 5, our m value, or lambda as Excel calls it, and true because it's a less than problem. So here we're going to do equals expon, and then it starts to show up. And so our x, they call it x, I wrote s in the slide so to not confuse it with our random variable. So this is 5. And then I could just click on M over here if I did it this way, or I can type in 0.25, and then I want to use the word true. So I get a probability of 0.713495, or about 71%. Now, for the probability that a clerk spends between 4 and 5 minutes, because it's the area under the curve, I find all the area from 5 down to 0. Then I find all the probability of the area from 4 down to 0, and I subtract that off. And that will leave me with just the area between 5 and 4. So you kind of have to find 2 probabilities here and subtract them to get the answer to this type of question. So that's why I set the spreadsheet up this way. So you can do this in more than one way. You can find this probability for 4, same M value, still the word true. And then you can just subtract them over here. So you could say equals the 1 for 5 minus the 1 for 4 and get your answer. But you can also type it all into one cell. So EXPON 5, M, true, minus, same thing, EXPON 4, M, true. And again, you can type in the 0.25. So you get the same value here and here, depending on how you do it. But if you like multiple steps, just to get your brain organized and see where everything's coming from, you can do it this way, or you can type it all in one cell, if that makes sense to you. So the probability that a clerk spends between 4 and 5 minutes with a customer is 0.0814 or 8.14%. So on average, a pair of running shoes can last 18 months if used every day. The length of time running shoes last is exponentially distributed. What is the probability that a pair of running shoes lasts more than 15 months? And on average, how long would 6 pairs of running shoes last if they are used one after the other? So first, we know that oh my goodness, I can't move my face. There we go. Our mean, our mu is 18 because it says 18 months. And for this kind of problem, remember your units. For all problems, remember your units, but especially for ones that you might convert like minutes to hours or months to years. And if this said, what was the probability that a pair of running shoe lasts more than a year and a half, you'd have to convert that into months to make it all make sense. So anyway, our mean mu is 18. So M is 1 over mu. And so 1 over 18 is 0.0556. So what's the probability that a pair of running shoes lasts more than 15 months? Well, that's going to be Px is greater than 15. Now remember, when we do those greater than problems, it's 1 minus, because we want the area to the right of the number we're looking at, and our formulas find the area to the left. So 1 minus that will give us the answer we want. So we're going to type into Excel 1 minus the exponential distribution of 15, our M value, and true. So if we go back here, our mu is 18. So M, again, you can just type 1 over 18 like this if you want, or if you were going to use cell references like we did before, you would do equals 1 divided by and click on that cell. And so again, greater than problems equals 1 minus. And so EXPON, and we're going to do 15. And our M value, again, you can type that in, and then true. And we get 0.434598. So we would expect a pair of running shoes to last more than 15 months with a 43.5% probability, or 0.43. On average, how long would 6 pairs of running shoes last if they are used one after the other? Well, this is kind of a different problem, but if 1 pair lasts 18 months, 6 pairs would last 6 times 18 months. So that's 108 months. So this kind of problem we saw before with the nurse rings, if you remember from chapter 4. So you take your expected value or your long-term mean, and you multiply it by the number that you're looking at. So 6 pairs on average, 6 times 18 months, or 108 months. So the memorylessness of the exponential distribution. So in 5.7, that was the postal worker. The amount of time between customers is exponentially distributed with a mean of 2 minutes. If 5 minutes has elapsed, I don't think that's true. I think it was 4. If 5 minutes has elapsed since the last customer arrived, it may seem more likely for a customer to arrive within the next minute, okay? But with the exponential distribution, this is not the case. The additional time spent waiting for the next customer does not depend on how much time has already elapsed since the last customer. And that's called the memorylessness, the memoryless property. So the memoryless property states that the knowledge of what has occurred in the past has no effect on future probabilities. So that's not dissimilar to the idea of independence, right? When we talk about probabilities. So that is the end of section 5.3 on the exponential distribution.